Good day, everyone. Welcome to this academic presentation. Today, we are excited to present our research paper titled Performance Evaluation of Active Queue Management Algorithms for IoT Edge Networks. This study was conducted at the Federal University of Pará in Belém, Brazil, by our research group consisting of Yasmim Sarmento, Emmanuel Cruz, Diego Oliveira, Bruno Lopez, and Tainá Baia. Our work addresses a critical bottleneck in modern network architectures: how edge gateways manage the sudden accumulation of data packets from hundreds of Internet of Things devices. As IoT deployments scale globally, understanding the underlying queuing dynamics at the edge becomes vital to ensuring the stability of real-time applications, control loops, and critical telemetry systems. We hope this presentation provides a clear path forward for designing latency-aware edge infrastructures. To understand the core problem, let us look at the dramatic growth of the Internet of Things. In a typical edge network, we have numerous smart sensors and actuators transmitting data simultaneously. At first glance, a single temperature sensor, or a smart meter, sending a few bytes of data every few seconds does not seem to pose any threat to the network. However, when dozens or hundreds of these devices share a single gateway and attempt to push their packets through a constrained wireless or backhaul link, a massive buildup of data occurs in the transmission queue. This congestion leads to long queues, which directly translate into high latency. In network engineering, there is a classic phenomenon known as buffer bloat. Oversized gateway buffers may temporarily hide packet loss by storing everything, but they introduce intolerable queuing delays. This makes real-time telemetry data practically useless, as a delayed alarm or an outdated actuator command loses all operational value. The primary objective of this research is to perform a rigorous, simulation-based comparative evaluation of three prominent queue management algorithms: drop-tail, random early detection, commonly known as RED, and controlled delay, or CODEL. We want to determine which algorithm provides the most robust balance of performance in a constrained IoT edge gateway under varying traffic conditions. To make this comparison comprehensive and scientifically sound, we analyzed 6 key performance metrics. These are average packet delay, packet delivery ratio, network goodput, tail latency, represented by the 95th percentile delay, average queue occupancy, and finally, packet loss rates. By evaluating this multidimensional set of metrics, we ensure that our conclusions look beyond simple throughput, directly prioritizing the actual quality of service delivered to the end application. Let us analyze how each of these three algorithms operates under the hood. First, we have drop-tail, which is the standard, passive, first-in, first-out queuing policy used in most basic routing devices. Drop-tail is entirely passive. It accepts incoming packets as long as there is free space in the buffer, and abruptly drops new arrivals only when the queue reaches 100% of its capacity. Second, random early detection, or RED, introduces a proactive approach. It monitors an exponentially weighted average of the queue size. When this average queue length falls between two pre-configured thresholds, RED begins dropping packets early using a linear statistical probability to warn endpoints of congestion. Third, CODEL represents a modern, delay-aware paradigm. Instead of checking buffer size, CODEL monitors the actual sojourn time, which is the exact duration a packet spends waiting inside the buffer. If this waiting time persistently exceeds a target delay over a set time window, CODEL proactively drops packets to clear the queue and mitigate buffer bloat. To evaluate these algorithms under controlled conditions, we developed a discrete event network simulator in Python. Our simulation parameters represent a realistic, resource-constrained IoT edge gateway. We modeled 80 active sensor nodes generating aggregate traffic using a Poisson process to represent dense, intermittent edge communications. The bottleneck link capacity was restricted to 1 megabit per second, simulating a constrained cellular or satellite backhaul channel. The queue capacity at the gateway was set to 120 packets, with an average packet size of 512 bytes. For our active queue management configurations, RED was set with a minimum threshold of 25 packets and a maximum threshold of 90 packets, while CODEL used a target delay of 5 milliseconds and an interval of 100 milliseconds, aligning with IETF standards. Finally, we varied the offered load from a stable 0.35 to a heavily congested 1.60 of the link capacity, running each test across 12 independent random seeds. Let us look at the average end-to-end packet delay when our edge gateway faces critical overload, specifically considering the operating region where the offered load is equal to or greater than the link capacity. In this scenario, the differences between the algorithms are striking. The passive drop-tail policy suffered from severe buffer bloat, keeping the queue nearly full and producing a massive average delay of 484 milliseconds. The classic RED algorithm improved the situation, reducing the average delay to 349 milliseconds, but this latency remains quite high for real-time systems. CODEL, however, demonstrated exceptional delay control, keeping the average latency at only 105 milliseconds. This means CODEL reduced packet delay to less than one-third of RED and to nearly one-quarter of drop-tail, proving that a delay-based approach is highly effective at preventing packets from lingering in a long gateway queue. This line graph provides a complete view of the latency trends across our entire experimental spectrum, from light load to severe congestion. As we can see, when the offered load is low, between 0.35 and 0.85, the gateway is not congested. All three algorithms behave almost identically, keeping packet latency near zero. However, the moment the offered load crosses the saturation threshold of 1.0, the latency curves diverge dramatically. The drop-tail curve spikes almost vertically, immediately reaching its maximum queue-induced delay. The red curve also rises sharply, showing that its average-based thresholds cannot prevent significant buffer buildup under persistent overload. In contrast, CODEL's curve rises very gradually, maintaining a low, highly controlled delay profile even when the network is pushed to a severe overload of 1.60. This behavior highlights CODEL's superior capacity to dynamically adapt to intense traffic spikes. To summarize our key findings, let us review this comprehensive comparison matrix. When we evaluate packet delay, drop-tail ranks as high. RED sits at average, and CODEL successfully achieves a low delay profile. Interestingly, when we look at link goodput and overall packet loss, all three algorithms achieve high and comparable results under overload. This is an important realization. An active queue management algorithm cannot magically create more bandwidth on a saturated 1 megabit per second link. Therefore, under severe congestion, some packet loss is mathematically unavoidable. What CODEL does, however, is manage this congestion intelligently. It achieves excellent congestion control by proactively dropping old, stale packets early to ensure that the packets that do get delivered are fresh. This results in a massive reduction in latency while maintaining a goodput that is virtually identical to drop-tail. In terms of complexity, while drop-tail is incredibly simple, CODEL and RED introduce a manageable level of complexity that is well worth the latency benefits. While our findings are highly encouraging, we must also acknowledge the inherent limitations of our current simulation model, which pave the way for our future research. First, our simulator utilized abstracted physical and medium access control layers. In a physical deployment, the stochastic behavior of shared wireless mediums, such as Wi-Fi, LoRaWAN, or cellular networks, will introduce additional delays and collisions. Second, our model assumed Poisson traffic, whereas real IoT networks often experience synchronized bursts when hundreds of sensors wake up and transmit data at the exact same instant. To address these limitations, our future work will focus on two major areas: We plan to incorporate priority differentiation, such as differentiated services or DiffServ, to ensure that critical emergency alerts always take precedence over routine telemetry readings. Furthermore, we plan to transition our testing to highly integrated network simulators like NS3 or OMNET++, allowing us to analyze these queue policies in combination with full wireless stacks and upper layer protocols like MQTT and COAP.
In conclusion, our research offers three fundamental takeaways for the design of modern IoT edge networks. First, passive queue management like Droptail is entirely insufficient for gateways prone to congestion, as it inevitably results in buffer bloat and stale data. Second, when evaluating performance in IoT systems, we must look beyond basic throughput or packet delivery ratios. We must prioritize tail delay metrics, such as the 95th percentile latency, because a delayed packet is often just as harmful as a lost packet. Finally, Codel has proven to be the most robust and intelligent solution for latency control, successfully mitigating buffer bloat and keeping edge networks highly responsive. We believe these findings will guide engineers in building more resilient, time-sensitive edge architectures. Thank you very much for your time, and we are now open to any questions you may have.